camera first. All right, that should get all of it, I think. All right, nice. So this is going to be a problem solving session. All right. Let's just. All right, so I'm going to open it at the same time on here. All right. So we'll wait a little bit. If you have any particular problems you want me to solve, just drop them into the chat. Some people gave me some problems to work on. But if you have any things that you want to put into the chat, please do so. Oh my God, did someone already donate? Oh my God. Thanks, Jean, again. Thanks for your donation. I want to be able to, okay, there we go. Yeah, thank you for the donation. Is there a way I can keep the chat on screen? Yeah. All right, there we go. So, yeah, so let's do some context-free grammar problems. So context-free grammar. So remember that a context-free grammar has 4 things in it. So it's got a set of variables, and then a set of terminals. And sometimes the variables are called non-terminals, which is kind of weird, in my opinion, because there are other things that are not terminals. So it's not that these are the only non-terminal things, but anyway, I call them variables. We got a set of rules, and the rule of a context-free grammar is that we can replace some variable A with anything that you want. So the right-hand side could be anything, and the left-hand side is a single variable. And so it's a context-free grammar because in anything that we're deriving, it doesn't matter what's on the left or the right of this A that we replace it with. It's free of the context in which it is. And then we also have a start variable. Okay. So then what we can do here is let's try to make it, let's look at a particular grammar. So let's say that I have S going to A, S, B, or capital A, and A goes to, oh, I don't know, B, A, or AS. Yeah, so that's perfectly fine. So this grammar is obviously a context-free grammar. And so what are the 4 parts here? So the variables here, so the set of variables are going to be the things on the left-hand side. So that's going to be the S and the A. The terminals here, usually we denote the terminals as being lowercase, although they don't have to be. And in this case, they're A and B. So little a, little b. So the start variable we can denote to be either S or A. It doesn't have to be called S, even though in the definition we call it S, it's just a name. So the variable A could be the start variable if we want it to. So let's say that the S variable is the start one. So S is the start variable. And then the set of rules are going to be these things above. So what we can do with a context-free grammar is we can check whether a string can be made. Well, we can see that the string A can be made. So A is in the language of the grammar, And we know this because we can do a derivation of it. So I can do have s and apply a rule with this variable. So here, this s can be replaced with just the a here. And then this a can be replaced with little a. So this particular string is in the language of that grammar, which is nice. We can also get a whole bunch of other strings. So I could, for example, repeat this rule many, many times. And I can get, let's say, 3 A's on the front, 3 B's on the end, with a single A in between. So these two bookends right here are going to be just applying this rule 3 times. And then now, if we apply this rule 3 times, then I'm going to get 3 A's on the front, 3 B's on the end, and then I can go down into here and get the single A just as before. So we can generate a whole bunch of strings, obviously. So if you have any questions that you want to see done, put them into the chat. All right. So what are some interesting things that we can do with a grammar? Well, we can convert them into a PDA, a pushdown automaton. So let's say that we wanted to convert this thing to a pushdown automaton. And yeah, that's fine. So let's convert this thing into a PDA. And I don't know why this is a hard conversion for a lot of people. It's the most viewed video on my channel, one of my most viewed videos. But apparently a lot of people want to see this done. So I'm going to go ahead and do that so that I can get more views, obviously. All right. So the art of it's actually not really an art of converting a grammar into a PDA is that we follow a basic recipe. So the recipe is that we're going to have 4 base states. So the recipe is we're going to have 4 base states, and the names don't really matter. And then the second one, and we'll see how to do that. The second one, on the third state, what we're going to do is handle, if I can spell handle, that'd be good, handle each rule of the grammar as a looping set of transitions. And so here's the general structure. This is what the shape of the PDA looks like. So we're going to have 4 base states like this. So, and the last one's going to be a final state. That's the only final state in the whole thing. Then what we're going to do is, for each rule, we're going to have a bunch of transitions that go out like this. So something like this for each rule in the CFG. And actually the third thing is reading transitions on, again, the third state. And we'll see how to do that. But it's basically this structure. So you have 4 base states. And we can, it doesn't have to be exactly this, but it's a nice algorithmic way of doing it. 4 base states, 1 set of transitions that go out and come back on the third guy for each rule in the grammar. So we got 5 rules here, so we're going to have 5 things that go in and out. And we're going to have a bunch of self loops here for each input character. So for every input character, we'll have a self loop on the third state. And that's basically it, the structure. So where can we do this? Okay, I kind of screwed myself here. So, okay, I'll do it up here. All right, so we're gonna have the 4 base states. So here's the PDA that we're gonna make. So we're gonna have the start state, 4 base states, last one's final. That's the only final state in the whole thing. What are we gonna... All right, so what are we gonna do here? Well, the first transition is gonna be putting on a special symbol that we pop off at the end. So no transition is gonna read except for these guys, the ones that self-loop on the 3rd state. Every other transition will not read anything. So this one won't read. I can't pop anything because start empty. And then I'm gonna put on a special symbol. It doesn't really matter what it is as long as it's not in the grammar. And you only use it for this purpose. All right, and then at the very end, we're gonna do the exact opposite operation. Okay, so here we push on the special symbol, we pop it off at the end. So effectively, the only way to get here is if we only have the $sign on the top of the stack, and that can only happen because we're gonna push something on this guy, then what's gonna happen is we're gonna have to eliminate a lot of that stuff on the stack with the one thing on there, and that's the only way we could even potentially get to the final state and accept. So the thing that we're going to push is the start variable. So remember that this is the start variable. Okay. So what are we going to do here? Well, here we can't go to the final state directly because we have a start variable on top of the stack. So the only way that we could eventually get there is if we remove the start variable. But that would try to imply that we're trying to match up the characters of the input string to whatever this variable can make non-deterministically. So what we're going to do is by implementing these rules and these reading things here, we're able to match up the characters with some application of rules. So let's handle this because it's really easy. So all that we do here is we're going to match up the input character with the thing that is being popped off the stack. So I'm going to have a bunch of self loops here. There are only 2 terminals here, so I'm going to have A pop off with A, and push nothing, and then B pop up with B and push nothing. So that doesn't depend at all on the grammar, you just do that regardless. Because we're going to be producing terminals on the stack, and we want to match them up, because it's a context-free grammar. Whenever we produce a terminal, it'll never change, because we can only replace variables with other stuff. All right, so here we're going to match up the input character with what's on the stack. So if the stack's got some terminals on the top of it, those are going to be matched up with the input. All right, so then here, let's start implementing some of these rules. So the rule of handling these outgoing loopy transitions is to push the right-hand side of this rule backwards. So effectively, this is what's on top of the stack, the variable, and what we need to have put onto the stack is this right-hand side. So we need to have a transition that comes out, which involves popping, not the $sign, popping the start variable in this case, if we're handling this rule, because it's the start variable in this case. So we're going to push nothing, although you could if you wanted to, but so what we're going to do is we want the A to appear at the top. So the A appears at the top, so that means that we need to push on the B first. So B goes on first, then the S, then the A. So usually I'm more efficient at this, and what I do is I push the B on immediately, and then push on the 2 other things. So the next thing is the variable S, the next thing is the A. So I'm never reading except for those 2 transitions up there. Then we're going to push on the S. Oh, that was backwards. So epsilon, epsilon S, read nothing, pop nothing, push the S on, and then a transition back, which is epsilon, epsilon A. So pushing on this right-hand side backwards. Can I combine the first two transitions into one? No. So I can't combine these two if that's what you're referring to, because we have to pop first. Because if you have a transition that pushes and pops, does both, then you have to do the pop first. And the reason is, if you do the push first, then the thing that you want to pop is under the thing you just pushed, because you're dealing with a stack here. So therefore, you need to do the pop first. But if you start over here, that means that you have an empty stack and you can't pop anything. So you need to do the push here. But actually, okay, sorry, I'm totally wrong. Here, these two could in principle be combined because you have two pushes. The thing is that PDAs in the usual definition only allow one thing to be pushed. But you can have what is called an extended PDA, and this is what Sipser does, where you can push multiple things at once. And that actually makes this conversion a little faster, but it doesn't change anything. Because if you have a lot of things that you push at the same time, you can just break that up into a lot of transitions that push one at a time. All right. So what are the questions? Your video's fatten up my brain. Giga chat. I don't match the meme. Although, if you can find a video, photo of me, you can certainly crop me into a Giga Chad meme if you want to. But I'll give you permission. I used to hate TOC. Watching your videos gave me a clear idea on the concept. Can you please suggest how to follow your YouTube channel to get maximum what? It depends on what you want maximum of, but thanks for the donation, Meep. If you want to donate, there are links in the description, but you, of course, never have to. All right, so this is handling one of the rules. I'm not going to bother doing really any other ones because it's going to be exactly the same. So if we wanted to do the SA rule right here, we would do the same idea. We would have a transition that comes out, popping S and pushing the A, and actually that can just come back. But there are several equivalent ways of doing the exact same thing. Say like for this one, A goes to BA, then we would have a transition that comes out, popping the A, which is the variable on this side, on the left side, and then we would push the right-hand side. So then we would immediately push the A back on, and then push the B on, and that would handle this rule. And you would do the exact same thing. So for all the other rules, you would just have a loop that goes out every single time. You can actually combine some of these sometimes, not always. Here you probably can't because you probably don't have another rule that has S on the left side and a B that ends on the right side. If you did, then you can combine this, which is usually why I don't push anything here, so that I can combine things. But generally, for proof of correctness reasons, you usually want to have these be separate loops. But otherwise, it's identical to this. So it's completely algorithmic. We don't have to think about this too much. We have 4 base states. Push on $, push on the start variable, pop off the $, self loop on the third guy, which is for every terminal of the grammar. You read it and you pop it, push nothing. And for every rule, you have a set of transitions that go out like that, a set of looping transitions. Oh, so for the gate exam, so I actually, if you look at my videos, one of my most viewed videos is solving every single gate question. So if you can certainly find that, and I live solved everything. I've done every single theory of computation question. I've done every single algorithms question, all in one live stream. Actually 2, but certainly you can find those on my channel. All right, so. Okay, so if you want to see a certain problem that's done, put it into the chat so that, or whatever direction the chat is now, so that I can do it. I can do like PDA to CFG conversions. I can do pumping lemma questions, any context-free language question, any regular language question, any TOC, theory of computation question. I'm happy to do any one of them. Yeah, you're probably watching, you're probably subscribed to the channel because of the CFG to PDA conversion, which is one of my most viewed videos. And the thing is that I don't see what's hard about that conversion. It's the PDA to CFG conversion that's way harder. And that certainly is a lot harder to get your mind around. But that video is not as popular. I have no idea why. But anyway, so we can do some pumping lemma questions. We can do some PDA type questions, like making a PDA for something. We can make a CFG for certain things. Anything that you guys want to do. So mainly I'm here for you guys. Let's see. I'll see if there's anything on Discord. And of course the dogs are barking. I need to get a mic for this. Let's see. What about the Turing machine? Oh, I didn't answer your question. Can you talk about any question about Turing machine and like how to prove decidability? Sure. Yeah. So those are good questions too. Dependability. I'm not sure what that is. Yeah, but I can talk about decidability problems. Sure. So what's a good one? So the one that's usually covered, but it is nonetheless important. Actually, I'll do one that I have assigned before. So one of the problems that you show to be decidable is the equivalence problem for DFAs. So here you're given two DFAs, so M1, M2 are DFAs, and their languages are identical. Okay, so this is decidable. And I know at least 3 different proofs of why that is. There probably are other ways, but I know 3 for sure. But there's a similar problem that I have assigned on tests before, which I really like, which is this. Something I call sub-DFA. So it's same description for the machines. So these things are DFAs, and the language of M1 is a subset of the language of M2. Okay, so it's not identical to the equivalence problem, because the equivalence problem says whether the languages are identically the same, whereas the subproblem just says, is the one a subset of the other one? And that's a looser question to answer, whereas this is strictly. So if it's like M1 has 1 fewer string than M2 does, then the answer here would be no, but here would be yes. So it's a little bit, in some sense, easier, but one of the reasons I like it is that it's pretty much just asking, if we have some kind of specification written as a DFA, and we have a candidate solution to the specification, does the solution satisfy everything that the specification says you're allowed to do? So is there any behavior of the solution that the specification does not allow? And if you have DFAs for this, then it's a decidable question, which is pretty cool. So try to think about why that this is decidable. So I claim that this is decidable too. So the answer is actually pretty easy. If you know the proof for equivalence of DFAs, then the subproblem is actually really easy, because it's like basically just 1/2 of the equivalence problem. Because for equality, it's basically just asking, is one a subset of the other? Whereas here, we're only saying, is this one a subset of that one, but not necessarily the other way. So try to think why that this one is also decidable. Because it's not always the case that if you have a constrained version of the problem that's decidable, it means that the general problem is decidable too. It might actually be undecidable, but in this case, it happens to be decidable. All right, so no one really answered, so I'm going to reveal the answer. All right, so the whole point of this class is that you can actually get a whole bunch of tools to be able to prove things by looking at it in a different way. So the equivalence problem, another way of phrasing the exact same thing, is that the language of M1 is a subset of M2, and M1 is a superset of M2. So one is contained within the other. Well, what about here? Well, you're only stuck on this, Ryan. Well, there is another way to phrase this too. So M1 is a subset of M2 if and only if M1 and M1 intersection the complement of M2 is empty. It's an equivalent formulation. There are other ways you can solve this, but is that true? Yeah, there are other ways you can solve this. So this is one formulation. So why is this true? So if this is a subset, if one is a subset of two, then there's nothing in M1 that's also that is not in M2, because everything in M1 must be in M2. So here this is saying over here, everything in M1 and everything not in M2, there's nothing in common between those two. So there can't be anything in M1 and not in M2. So that's effectively a proof of why that's the case, why this is true. So why is this decidable? I'm not going to write the whole thing, but basically what you do is you make a DFA for this guy, because this is a DFA, this is a DFA. The complement still makes it a DFA. You can just invert final states. And here, the regular languages are closed in an intersection. So you can actually make the DFA for the intersection. So I can make a giant DFA for the left side. Well, then I just want to know if that giant DFA accepts nothing. And then I can just run the emptiness decider for DFAs. So this is decidable for that reason. There are other ways you can prove it too, but they're a little bit more complicated. All right. All right. So someone's, who said that? Andrew said, if I construct a DFA from both M1 and M2, if both recognize some languages, then the DFA will be the empty. Well, you can't prove it because you don't know what these two machines are going to be. So it could be that these two machines are identically the same language, or they might be totally different languages. We don't know necessarily. It's just that we have a decider to check that. Because making the DFA takes a finite amount of time. That's probably something I should have checked. So making the intersection of the DFA takes a finite amount of time because you can just run the product construction, which takes a finite amount of time. So I can make the DFA in a finite amount of time. So then checking whether or not that DFA accepts nothing, there's a decider for checking whether or not that language of an arbitrary DFA is empty. And so this can certainly be done. All right. So I'm going to get rid of this. You know it's a problem-solving session at this point. All right. right, so someone put a pumping lemma question in. So let's see. Okay, so pumping lemma for regular language, okay. So we have some language L, and what is it? It's C, pound sign D, pound sign D, pound sign E, oh, not empty, E, where C, D, E are in A, B star. I think that's what you wrote. Yes. All right. So this is not regular, and yeah. So I'm trying to think of the most efficient way to prove. Okay. Yeah. I see. So this is not regular. It's actually not context free either. Actually, let's do not context free. Because if we show it's not context free, then it would automatically prove that it's not regular too. Okay, so if it's not context free, well, the only real tool that we have to use is the pumping lemma for context free languages. If you know Ogden's lemma, which is a video of mine that I recently did, you can use that. Let's use the pumping lemma. So let's see. So we have this string right here. Sorry, this language. And every pumping lemma proof starts off with supposing that it was not true. Suppose that this statement right here is not true. So suppose L were a context-free language. And then eventually we got to get some contradiction. So actually I'm going to put over here contradiction. QED. We proved what we want to prove, assuming we get down to there. Okay. Okay, so here we have a context, we're assuming we have a context-free language. Then what the pumping lemma for context-free languages says that there's a context-free grammar for the thing, or a PDA or whatever. If you know what a recursive automaton is, that also works. But we know that there's like say a CFG for it. But in particular, there's this particular constant, this pumping constant, P. And the important property of this is that this value of P allows you to copy and paste parse trees, sub-parse trees within a particular parse tree. And that's what the pumping part is about. You're copying and pasting parts of the parse tree around. So this constant P, once you get above that threshold, then it guarantees that you can do the copy paste thing. So the lemma says that this number exists if we have a context-free language. So there exists a pumping constant, I'll write it here, P for L for this language. Okay. So one of the important things that we need to do is we need to actually get a parse tree, because once we get above this threshold, we need to work on parse trees. So you need to have a parse tree. Well, to get a parse tree, you need to have a string that the grammar can make. So so how do we do that? Well, we need to pick a string that's above this threshold in the length. So it must have length at least P, so that we can guarantee that we can do the copy paste thing. It looks like I'm doing something spooky there, but so we need to have the string be of a certain length, and what we need is that the grammar can make the thing. So in other words, that the string, whatever we choose, is in this language, because we can't actually we can't make a parse tree if it's not in the language. So we need to pick a string that's, in the language and length at least P. So here, now let's look at our language. So the language says that the C and the E part can be whatever, and the D part can be whatever. The important thing is that there's a duplicate of D here. So effectively, this C and E have absolutely nothing to do with the rest of the, they don't have anything to do with anything else. So there's nothing in common between them. So effectively, we can just remove the C and the E part of here. So these are just arbitrary strings by this, and D is an arbitrary string, but we can just throw the C and E out. So let's pick a string here. So I'm going to choose a string W, and you don't have to choose this particular string, but I'm going to pick this. So pound sign, the pound signs have to be in there. So A to the P, B to the P. And then now so this is the D right here. And so I'm going to have the same thing twice. So I'll do in black marker where the parts are. So the C part is right there. Is an empty string, which I'm allowed to do because C can be empty. Same thing with E way over here. It looks like I'm drawing a character, but I need you to actually see it. So this represents the empty string. This part is D, and this part is D also. So we know that this string is in here because here's the C part, here's the D part, here's the D part, here's the E, and it matches this. If you have any questions, put them into the chat. You don't have to stay silent if you are confused by a certain thing. I just happen to talk too quickly sometimes. All right, so here, does it have length at least P? Well, it does, because each of these little runs here have length at least P, and so therefore the pumping lemma applies. And so therefore we should be able to pump this string according to the rules of the pumping lemma for context-free languages here. So the important thing here is that we need to look at all decompositions. I swear, I underline all and capitalize it sometimes, and people don't follow this. You have to show all decompositions. So we need to look at all decompositions of that string W into the 5 parts for the pumping lemma. Maybe your instructor calls them differently, but such that the 3 middle pieces aren't too long in total. So the length of those 3 is at most P in total. The second and the fourth piece have some character in them. So another way of saying that is that the length of the second and the fourth piece together have at least one character. So it's not the case that V is empty and Y is empty. All right. So what are all the possible decompositions? Well, let's see. So I'll break this into cases. So case 1, which is actually going to be a really easy one, which is noting that we have exactly 3 pound signs in any string in the language. So therefore, if either one of these 2 pieces have a pound sign in them, then what I can do is pump up the jam. I can pump 1 additional copy of V and 1 of Y, because I need to pump the same number. And so therefore I'm going to get at least 1 more pound sign than I had before. Well, I had 3 to start with, and every string in here has exactly 3. So therefore I'm going to get at least 4, and so that's going to give me a string not in the language up there, which is what we want. So in case 1 is that V contains V, actually I'll say V or Y contains a pound sign. And so we have that U, V squared, Y squared, Z. So this is 1 more copy of V and Y each. So this contains at least, actually you can say exactly, but it contains at least 4 pound signs. So is not in the language. And so if we have a decomposition of that type, therefore we can pump out of the language pretty easily, which is nice. So then what are the other cases? So one case is where the V and the Y part are on one side here. So the V, let's say V and Y are both on the left side. It'll be similar on the right side because this section and this section have to be identical. So therefore, let's say that case 2 is that V, actually it's both in this case. So V and Y on one side of learn to write, Ryan, of the middle pound sign. So that means, so let's draw what that looks like. So we have pound sign, a bunch of A's, a bunch of B's, pound sign, a bunch of A's, a bunch of B's. So that means the V, let's say, is here, and the Y is there. That's just one possibility. There could also be many other possibilities. Okay, so then what we can do is the same trick, but for a different reason. So if I put more of the characters on this side here, I'm not touching any of the characters over here. And so therefore, these two sections aren't going to be identical anymore because they were identical before. But they need to be identical in order to be in the language here. So here, if we look at uv squared x, y squared z, so this has more characters in one run, I'll write it this way, on one side compared to the other. And so it's not in the language as a result. But that doesn't handle every single possibility, unfortunately. So we handled the case of where it has a pound sign. That was case 1. The second case is where they're both on this side or both on this side. So the only other possibility is that V is on this side and Y is on this side. So that's case 3. It'll actually be almost identical, perfectly spaced out, which I did not plan. So V on left side, Y on right side. So again, let's visualize. So a bunch of A's. So the V, so here's where we're going to use this property right here. So we're going to use this property that says the V and the Y part in total have at most P characters. So that means that since this run right here, the B part, not the whole thing, the B part, has exactly P characters according to this, although it just needs to be at least P, but it has P characters here. So that means that the V part, which is on the left side, has to be in this region right here. It can't touch the A's over here. And that's what's crucial, although it doesn't really matter too much, but it'll help. So the V part is right here. And for similar reasons, the Y part is in here somewhere. Is in the A's there. Because V and Y in total have at most P characters. So the Y part can't lead into the B's over here. Because the V part must be on the left side. All right, so then what if we pumped up again? So here, let's look at u v squared x y squared z. So then what's going to happen is we're going to put more B's here on the left side and more A's on the right side. But we're not going to touch the outer sections here. And that's what helps us. So if we have, let's say on the left side, so some number of A's, but a lot of B's, and then a lot of A's, not necessarily the same number, but a short number of B's, then there are two ways you can go. You can say that this side has the same number of A's as PA's, and this side has more than that. And so therefore they can't be the same. And that'll be enough. You can do the same thing with the B's too. It'll work exactly the same. And so this is not in the language anymore, because the two sides just aren't identical. Because they have, another way you can show it is that one has more of one character than the other one, and that's another way you can go. We don't know necessarily about the lengths here, because it could be that V and Y are the exact same in length. So therefore, if we pump more in, the lengths of the sides are the same, so you can't say that the lengths are going to be different. It'd be nice if they were. But structurally, the strings are different. So it's actually important that this language is over AB star instead of just like A star, because this language would actually be it would be context free if it were would it be? Yeah, it would be. It'd be because you can just expand. Yeah. So this would be context free if you had one character. But since you have two characters, that allows us to get this final argument in. All right, so that proves that this language is not context free, and answering the original question is not regular. So therefore we got that. All right, how to prove that for every regular language, the no proper prefix is in L. I've done a video like that on the channel already. I forget the name of it, but it's like prefixes are regular or something. But this question is about proper prefixes. So try to think, how do you go from recognizing the prefixes to getting all the strings that are not prefixes, and then getting the ones that are not proper prefixes. It's just a chain of things that you have to do. You could prove this directly, but it's often easier to chain things together. All right, so I got a proof question about even Turing machine. Given a Turing machine over some alphabet, does there exist a string of even length such that M accepts input W? How can we formulate this language? And how can we show that this language is recognizable? All right, so we can do that. Hope you're all doing well. Where did I put my water? I need a drink. Yeah, that was a nice pumping lemma proof. It kind of required you to do several cases here. But essentially, it's very identical to the W #W proof that is in the Sipser book. Because we can just chop off two of the strings here, because they have nothing to do with the rest of the thing. So let's see. So you're asking about even Turing machine. Given a Turing machine M, does there exist a string W of even length such that M accepts W? So we can say even Turing machine. So are you given the Turing machine? Yeah, so you're given the Turing machine. So this will be the description of some Turing machine and input W, such that, or is there, oh, you're not given W, okay. So there exists some W with length of W even, and M accepts W. And this is undecidable by Rice's theorem. Because if you happen to have two Turing machines with the exact same language, then that would mean that either both of them accept some even length string or both don't. And it's non-trivial because if you pick the Turing machine that doesn't accept anything, then this machine, then it's not in here. And if you pick the machine that that accepts everything, then it's in here. I have theory exam next week. Your channel makes me love this subject. Thank you very much for that. I get, not necessarily me, but I hear a lot of hate comments about this subject, and it just makes me sad. So seeing people love this subject is what makes it all worth it. All right, so this is this recognizable? Yeah, so this is recognizable. And the reason, I'm not going to go into the full details because most people are worried about the context-free stuff now, is you basically can just dovetail across all of the even length strings. So look at the ith even length string and run all strings from that point back, so all the strings up to that point for I steps each. And if at any point for some I you accept the string, then you answer yes, and that's all you have to do. So it's just a classic dovetailing problem. All right. Let's see. Can you prove that the class of context-free languages is closed under homomorphism? Sure. So what is a homomorphism? So I'm going to give the easy answer for what a homomorphism is. There's a more general answer for what it is, but essentially what it is a function that will take a character, so like some character C, and output some string. So this thing is a character. And actually there's also one for the empty string too. And that'll output some string too. So effectively, it's mapping a character or the empty string to a whole long string or maybe a short string or something. And the alphabets don't necessarily have to be the same, but that's not so important. All right, so then what we want to say is that if L is a context-free language, then and H is a homomorphism, then we look at this language, which is apply H to every single string in the language. So take every single string in the language, apply H to it, and just keep all the strings that come out of it. And so then this thing, that language, is a context-free language. So I actually assigned this question on an exam one time. It's a really nice problem, and it's actually really easy to do. So all that you need to do, so the proof of why this is true is actually very, very short. So what you do is you look at it, take, if I can spell the word take, that's the hardest part of the proof, is being able to spell, I swear. So the proof here is take any context-free grammar. You can do this with a PDA too, it doesn't have to be a context-free grammar. Let's call it G for this language. Then what we do is replace every terminal in G, every terminal in some rule of G. Let's call it T for terminal. So every single terminal, we're gonna replace that with H of T. And that's it. It's actually surprisingly short. So what's an example? So if we have a grammar that looks like this, so like, I'll do a really simple one. So let's say we have an h function, which for the empty string will map to 0, 1, 2. And then h of a, let's say, will go to just 1, and h of b will go to, oh, I don't know, 2, 2. So then all you do in this grammar is just do some replacing. So you're going to get s going to, so the a gets replaced with 1, the s doesn't change, b gets replaced with 2, 2, and then the empty string gets replaced with 0, 1, 2. And so if we look at like some string that this makes, so let's say like AB, so this thing makes AB, so AB, and then translated over, that's 1, 2, 2. No, sorry. Okay. Yeah, I'm actually wrong about this. The empty string has to map to the empty string. Yeah, so this has to map to the empty string. I forgot about that. So here this will be empty. Yeah, and then now it carries through. I thought that it didn't make sense to me when I was writing it, but yeah. The rules of a homomorphism are actually, you can decompose any string that you want to apply h to into the individual characters. And in order to get that to work, you need h of epsilon to not do anything to the result. And the only way you can do that is with the empty string. So that's the only thing you can do. All right. Yeah. So context-free languages are closed in their homomorphism by this. You can do the same thing with an NFA, for example, to get the same type of result for regular languages. Pretty interestingly enough, decidable languages are not closed under homomorphism. And I have a video on the channel which gives a nice reason why. It's actually not so straightforward as to why that's the case, but it's a pretty cool result. All right, what other questions do you guys have? Do you have more context-free questions? Do you have more pumping lemma questions? I know a lot of you have some exams that are coming up soon, so if you have questions, that's why I'm here. Can you show why context-free language is not closed under intersection? Sure. So, yeah. So we know that the language, I'll do A, B, C. So A to the n, B to the n, C to the n, where n is at least 0, is not a context-free language. So the trick with these is we want to have two context-free languages whose intersection is this guy. And there are actually a bazillion ways to approach this. There's not one particular approach, but I'll show you the prototypical way of doing it. So if we have, I need to have two languages whose intersection is this. So the general way we do this, which is what I'm going to do here, is intersection of two different strings that have two different properties are going to merge and have have both properties. So the properties in this case are that the number of A's and B's is the same and the number of B's and C's is the same. So I'm going to make two languages. So A to the n, B to the n, so same number of A's and B's here. And then any number of C's that you want, so let's say P. So n and p have nothing to do with each other. So both of them are just numbers. But the A's and B's have the same number. And L2 is going to be the opposite scenario. So the p is going to move front, and then the n's are going to go to the end. And ends go to the end. Terrible professor jokes. All right. So then it's pretty clear that the intersection is going to be the top guy, because here any string in the intersection must have the same number of A's and B's and the same number of B's and C's. And that's the transitive property of equality there. But anyway, so what we need to convince ourselves of is, are these two things context-free? Because if I just arbitrarily made these languages, then that doesn't imply anything. So these are both context-free. And it's actually pretty simple to see why, but I'll make a grammar for one of them, and I'll let the interested reader make the grammar for the other one. So the reason why, say like this one, is context-free, this language, is because we can do A to the n, B to the n by itself in a grammar, and then the number of C's just doesn't matter whatsoever. So let's make a grammar for L1. So CFG for L1. So I'm going to have a start variable. So that's my start variable. Well, here, I know how to do the A to the n, B to the n thing. So what I can do, so there are several ways you can do this. There's not one way. So what I'm going to do is I'm going to have this go to two variables. So why two? And why are they concatenated together? Well, here, the A variable is going to make the things that are the same, the A to the n, B to the n part, and then the B variable, actually I'll call it C. So C. So the C variable is going to make any number of C's that we want. So we can handle that straight away by saying C variable, make any number of C's that you want. Well, that could be the empty string, so none, or you can make one more than you have already, and then just make, and then recursively make some more. For the A variable, we know how to do that. So that's little a, big A, little b, or empty. So the A variable makes A to the n, B to the n for any n that you want. And then the C variable makes any number of C's that you want. And I concatenated them here because these two things are put together. And the grammar for L2 is basically the same. It is very similar. So you would just basically swap these and then change the C here for an A, and then these for B and C, but it's the same, basically. Same structure. Yeah, so they're not closed under intersection. They're not closed under complement either, but that proves a little bit more tricky, but the same idea. For complement, you look at the complement of this language, and then you argue that the resulting thing is context-free, because you know that this thing is not context-free. All right. What other questions you guys got? What kinds of problems do you guys have? Let's see, what time are we at? All right. All right, so I'm not seeing any other questions, so I'm gonna end the stream here unless one pops up in the next few seconds. So thanks for watching. And next week I'm going to do another problem solving session because I know a lot of people are taking exams. And as always, I will see you all next time. Oh, there is one more question. What's your personal email address? In the comments down below. Sorry, in the description of the video. It should be there. But if it's not there, check any video on the channel. My email's in there. Although you should probably use the Discord. You probably shouldn't email me directly, but if you really need to, for whatever reason, it's in the description. All right, I think that's enough for today, so I'll see you next time. Thanks.